Uh, Good morning, good afternoon, welcome wherever you're joining. My name's Oliver Gunasekara. I'm the CEO and co-founder, and I'm going to talk about the inconvenient facts around LFP batteries. So welcome to everybody for joining. We'll take questions at the end, but let's get going. So the first thing to kind of say is that, I assume most people are familiar with what is LFP, what is NMC, but just a very simple explanation. These are chemistries that are used in the cathode of a battery, typically a battery that goes into an electric vehicle. LFP stands for iron phosphorus, so it's an iron-based chemistry on the cathode. And NMC is a nickel, manganese, and cobalt-based chemistry. And NMC has historically been used, but LFP is, I would say, at its hype on the cycle. It's gained a lot of traction. Tesla started to deploy. It's been used in China for a long time. And it has some good characteristics, but it's definitely at a very high hype level. And so I'm going to try to talk about it from a more practical point of view and maybe dampen some of that hype. Now, when we look at chemistries that can be used in batteries, there are really two mainstream and kind of two emerging. So NMC, as I said, is the nickel, manganese, cobalt. It's the mainstream of the market today, about 60% by kilowatt hour. And it has the best energy density. So energy density, you can see here, 250 to 350 watts per kilogram. And that's what we call the gravimetric energy density. So it's based on weight. And weight is really important in an electric vehicle because the heavier the battery, the more energy you need to just move the battery around. LFP is an iron phosphorus-based chemistry. It doesn't use nickel or cobalt, but it has substantially less energy density. So you can see 170 to 220 watt hours. So that means about a third less range. Cost-wise, you'll see LFP historically has been a lot cheaper, and that's partly why it's been attractive to people. Now, on the emerging chemistries, there's a variant called LMFP. This is where they take the traditional iron phosphorus and they add manganese into it. It's emerging chemistry. It's not really deployed at scale yet, but it's coming, and it does improve the energy density somewhat, but not as high as NMC. And then sodium ion or Na ion. This is a brand new chemistry that doesn't even use lithium. It has much less energy density. In my view, not very good fit for a vehicle, but probably a good fit for stationary storage. And again, of course, because it doesn't use lithium, it has the potential to be lower cost. So this is kind of an overview of the chemistries. But what I wanted to talk to now is about some of the perceptions that are out there around LFP and NMC. Specifically these 5 perceptions, and I'm going to go through slides on them. I think there is wisdom out there. There is a perception that LFP is much safer than NMC. And so when you look at the pack level energy density, so not at the cell level, but at the pack level, because it's safer, you don't need as much structure around the battery pack. And so you save that weight. And so you close the gap on energy density. And so the ranges are the same. We'll talk about that. Number 2 is that LFP is always going to be much cheaper because it doesn't use nickel and cobalt. Number 3, Inflation Reduction Act. We know there's a large amount of subsidies to building in America. That's both the actual construction of the batteries and the plants. And there are a lot of rules now about what qualifies and what doesn't. And you'll see getting Inflation Reduction Act subsidies for LFP is going to be quite challenging. Number 4, the ESG, environmental, social, governance issues around the supply chain of nickel and cobalt are poor. And so that's why LFP has a safer supply chain. It has less environmental and social issues. Again, we'll talk a bit about that. And then finally, going with LFP doesn't have any compromises. you'll see that, we think there will always be a range of chemistries. They all have different trade-offs, and there are definitely some compromises with LFP. So let's go in and go to number one. So, here is a paper that was recently released. And, this paper is looking at the safety of LFP chemistries. And it is true that from the thermal runaway, i.e. the potential for the pack to combust, it needs a lower temperature than NMC needs a lower temperature, meaning the chance of an NMC going into thermal runaway is increased. And that's why a lot of people claim that LFP is significantly safer, because you don't need to achieve as high a temperature with an NMC cell before it starts to go into thermal runaway. But unfortunately, that is only one of the characteristics of the safety issues of cells. It's not just about thermal runaway. It's also about the explosion risk from the vented gases. And what this paper is showing, and there's a link when I share the slides, is that LFP actually vents a lot of gas, and these gases are hydrogen, ammonia, methane, ethylene. These are gases that are highly combustion and highly explosive. And NMC does not vent anywhere near as much of these gases, and it tends to vent more carbon dioxide and monoxide, which have no real chance of explosion. And so as a result, when you design the pack, you have to factor in to protect against this risk of explosion from these gases. And because this explosion risk is so much higher with LFP, you cannot cut down that pack design. And so the people that argue LFP is so much safer, we can save that cost and weight in the pack design. And so, yes, at the cell level, we have a big energy density difference, but at the pack level, because we've reduced the need for safety requirements, the pack level energy density is almost the same. That's absolutely not the case. You really do have to protect against the explosion risk from fire. And here is a big explosion that actually happened in Beijing, where an LFP fire actually killed 2 firefighters. And they did a lot of analysis over this, and it was really the venting gases that exploded that caused this big problem. So definitely LFP will not be able to achieve the same energy density as NMC, even at the pack level, despite a number of the LFP vendors claiming this is the case, because they're not factoring in the vented gases and the likelihood of those gases exploding and combusting. So that's the first truth. Let's talk about number 2, which is really around cost. And historically, there has been a decent delta, maybe $10 to $20 per kilowatt hour difference in cost between LFP and nickel-rich chemistries. And obviously, your iron and phosphorus are cheaper than nickel and cobalt. But this is very recent data. This was from Benchmark Minerals Intelligence conference just last month. And you can see here, NMC 811, that's the ratio of nickel to cobalt and to manganese. That's the latest chemistry in the nickel-rich side, is achieving almost parity now with LFP. And so that price differential may not always be there. It also really ignores the fact that there's a large amount of recycle value in an NMC cell at its ends of life. So nickel and cobalt are highly recyclable. We recycle lots of it today. It has a significant value. The challenge with iron and phosphorus is that it's very, very low cost. It does not have any recycle value. The lithium does, but it's very difficult and expensive today to extract that. And no one is really doing it in a cost-effective manner. And so if you factor in the lifetime value of the cells, You may have to have a negative cost to recycle LFP. You may have to be paid to recycle LFP, whereas you can generate revenue with nickel rich. Also, LFP prices are going to be and continue to be driven by the lithium price. That's the most expensive metal. And lithium has huge demand, which I'll show on the next slide. And then I'm also going to talk a little bit how deep sea mining, given the size of the resource and the economics of the resource, can continue to drive the cost of nickel and cobalt down. So looking at lithium supply, lithium prices have gone up, and that's what's closed the gap in the pricing, because you actually end up using a different form of lithium and a slightly more expensive form, or it can be, in LFP cells, given on the demand. And demand for lithium is going to grow 9x by 2030. That's higher than any of these other metals. And so it's expected that lithium price will continue to rise. That, again, is going to lead to LFP being more expensive. Now, if we take about the seabed is obviously what Impossible Metals is focused on. And, some ask why go there? Well, there's a simple answer. It's the biggest resource. If you look at this graph, you can see the amount of nickel, cobalt, and manganese in the ocean compared to what we know about on land is just much, much larger. And that also has the potential to affect the prices going forward. Another factor when you look at a mine and you look at a resource is, where is the resource and what is the grade? And one of the nice attractive markets for the seabed is that we have very, very high grade resources. So the nickel grade is about 1.3%. That's compared to, say, 0.2, what you find today in new mines. And we don't have to do any tunneling or cutting. In addition, we actually get at least 4 metals in one resource. That really drives the economics, because instead of having to go to 4 mines, we can go to 1 and get all of the metal. And so if you factor in the equivalent value, when you get a credit for the other metals like copper and cobalt and manganese, it's 3.2%. That's huge. We also don't need to build a lot of infrastructure. One of the beauties of the seabed is the fact that we can reuse ships and ports versus, say, a mine very, very far north in Canada. We would have to build a highway, a train line, a village, a power plant. All of that adds cost, it adds risk. We don't need to do that in the ocean. And then with our technology of selective harvesting, we don't have to rehab the mine. And that is cost that a traditional mine has to bear, typically hundreds of millions of dollars put into a government bond at the start of the process. And that then is used at the end of life, but that has to be paid for. And then, we believe that because there is no one's backyard, because we don't need all of this infrastructure, the environmental permitting and cost will be less, and it will be quicker than the average of 16 years to permit a mine on land. So just to kind of summarize, there are 3 different options for where to get our nickel and cobalt from. And today, almost all of it comes from land-based mining. Of course, we can recycle, but that takes time. There isn't enough material available for recycling in the short term, but in the long term, there is. But on the land-based mining, we've basically looked at some new mines. This is a company called Gigametals, and their cost in their feasibility study is about $4.65 a pound. That's what it costs them to get this metal out of the ground. And depending on where the mine is, if the mine is in Indonesia, there will be rainforest disruption. If the mine is a cobalt mine in the Congo, there could be child labor. So you can see how there can be human rights impacts and environmental impacts. Now, if you look at the traditional approach to deep sea mining, which is dredging, say someone like the Metals Company and Allseas, they have a lower cost because of the resource. They're going after about $1.23 a pound. But our technology, because it's scalable, because we don't need a dedicated ship, when we plug that into our economic model, we're coming out at about 31 cents, so significantly less. And again, we don't believe there will be any human rights issues because no one actually lives on the ocean. And the environmental impacts, I think, will be less. There will be some, but with our technology, we're trying to minimize it. So because our cost base is going to be so low, we can allow the metal prices to come down and still be very, very profitable. And that will affect the economic discussion around LFP versus NMC. Now, let's talk to IRA subsidies or Inflation Reduction Act. This is a massive piece of subsidies for the domestic supply chain in North America. Now, LFP was invented in the States. Initially, it was a US technology, but it's been commercialized in China. It's the dominant architecture. And if you do a simple patent search on Google Patents, there are over 100,000 patents. These are US patents, but they've been filed and owned by Chinese companies. And so that means that to actually build an LFP cell and get it to yield and to get it to perform, you don't need just the fundamental invention. You need all of that implementation patents. And today, almost all of it is owned by China because they make something like 99% of all LFP cells. And, recently the Treasury came out with its interpretation of the rules. And, what it said is that, they have this wording in the legislation called foreign entity of concern. And so they've recently now defined what that means. And it basically means, China, Russia, North Korea. And if those companies have 25% or more ownership in the venture, then you will not qualify. Now, there are a lot of other things you have to qualify, like making the batteries in the US, refining and processing them. But basically, that makes it very, very difficult to partner with a Chinese company, to qualify and still get the IRA. And then, of course, there are US startups working to make LFP here, but I think they have two issues. The first issue is they've got to work around the 100,000 Chinese implementation patents. That's not easy. And then the second thing is that the automotive industry is very conservative. They want to see about 6 years of samples out of a new factory from a new vendor before they will qualify it. And so that is a big bar, in fact, achieving both. So working directly with the Chinese, I think, will not qualify. Working with a US startup could qualify, but they've got to work around the 100,000 patents and they've got to go through the 6 years to get qualified. And because of this, you've just seen Tesla very recently come out and say, look, we're losing some of the federal rebate on some of our vehicles from 2024 because of this new rule. And this is because they're using LFP cells in those. And so the $7,500 that the consumer today in North America can get back is going to be lost for some of their portfolio because they're using Chinese LFP cells. And so, my view is that it will be very difficult to qualify for IRA tax rebates if you're using LFP, because if it's a Chinese company and they have more than 25% ownership in the venture that you're creating, it will not qualify. And if it's a startup, they've got to work around all of the patents, US patents, but owned by China, and they have to create all of the different samples that takes many years to actually convince the automotive to get into production. Okay, now let's talk about number 4, which is really the ESG impacts of land mining, and specifically nickel and cobalt. Of course, this can occur in any type of mine. Iron and phosphorus still has to be mined, as does lithium, but there are some well-documented challenges with nickel and cobalt. And here you can see the picture is actually a mine from Indonesia. And that mine was a rainforest. And so the rainforest has been removed. The nickel laterite ore exists directly below the rainforest. Typically, that removal was done with diesel-powered dump trucks and diggers. And then, once the deforestation, the biomass, the biodiversity, the carbon sink is all released, you now have to then process this ore. And this is a low-grade ore. So the traditional approach is to use high-power acid leaching. It's called HPAL. And unfortunately, it leaves behind large amounts of toxic waste, which today they dry stack. But in a seismic environment, there's a high chance that that could then be disturbed. Previously, they would dam, and even earlier, they would dump this toxic waste into the ocean. If we talk about Africa, something like 70% of the world's cobalt comes from the Congo. And unfortunately, there are well-documented artisanal mining. Something like a third of all mines use people to do the mines. And there are many, unfortunately, deaths and injuries, often with children, as they dig deep into these tunnels to get paid $1 to $2 a day. So these are true issues today, but they don't necessarily have to be issues in the future. As I've mentioned, the seabed is a huge resource of these metals. And this is just a pie graph to kind of show how much of the seabed would be impacted. And what I took here was the total seabed area. And you can see the trawling. So that's the form of fishing that can impact the seabed. And it uses about 1.4%. And there are some links to the source data of the ocean every year is used to do trawling, and obviously has some environmental damage. Now, initially, I plotted the amount of area that would be used by nodule collection, but it was so tiny, I couldn't even get it to show up. So I then said, let's take that amount and times it by 50 years. And this assumes about 50% of all of the exploration permits that have been issued over the last 30 years are producing. And now let's take that annual amount and times it by 50 years worth of mining, and you still get less than 0.5% that would be impacted of the ocean. So it's a pretty tiny area in the big scheme of things. And what we don't realize is that about a quarter of all of the wild seafood that we eat is caught with this bottom trawling technology that unfortunately has huge impact. And this fishing is done at shallow depth, whereas the deep sea mining is done at very deep depths. And there's a very big difference in the amount of marine life that exists when you go thousands of meters and where no light can reach. So that's kind of the first thing to say about seabed mining, nodule collection. But at Impossible Metals, we want to go even further. So this is the first generation technology. This is the technology that is called dredging and riser pump. It was first tested in the 1970s, and it's the technology that everyone else is using. And it really does have a big impact. It gets lowered to the seabed floor. It generates sediment plumes. It vacuums up everything in front of the machine by injecting water into the seabed itself and then removing the top few centimeters and then sucking it up the pump. But this was what we call first gen. It was tested in the 70s. There are other companies that have tested it in the last few years. But we think there's a better way. And when you look at the different types of ways that you can do seabed mining, compared to land-based, we know that you could basically be carbon neutral. We know that the habitat is being destroyed. There's biodiversity loss. We think that the dredging will do better on human rights because people don't actually live there. And with the right processing technology, they can avoid the need for toxic tailings. But you can't really recover the seabed after it's been dredged, and it is more expensive. But with our technology, we really took all of the concerns that were being raised by marine scientists and others, and really architected a collection system that could minimize all of them. And so I want to just show you our latest 3D animation of how our system works compared to the dredging.
At Impossible Metals, we are developing autonomous underwater vehicles that are launched from a ship to the ocean floor, where there are vast fields of rocks, called nodules, that are rich in metals that are critical for low-carbon technologies, like batteries. Hovering over the ocean floor, artificial intelligence uses cameras and robotic arms to pick up each nodule individually, minimizing sediment disturbance and avoiding visible life, while leaving behind a percentage and pattern of nodules to preserve biodiversity and ecosystem services. The collected nodules are stored on board, and once the vehicle is full, it returns to the ship. The recovery crane is designed with motion compensation for fast docking, giving the vehicle a stationary target. Once on board the ship, nodules are offloaded and the battery is swapped before the vehicle's next trip to the seafloor. A key part of this system is that the fleet of underwater vehicles remains at sea. As one ship is filled with nodules, another arrives to continue the collection operation. Our highly scalable fleet is designed to reach the high production levels required to meet market demand.
So as you can see, it's a completely reinvented architecture for deep sea mining that really has taken the precautionary approach and kind of baked it into our architecture.
At
So, as a summary to compare to the dredging, we do not use the dredger collector machine. We use a fleet of these autonomous robots that actually hover. And to move the material up the water column, we actually use the payload as the vehicles go up and down. And one of the big innovations is that we don't need a dedicated mining ship. And that saves a large amount of money. We basically reuse the bulk transport ship. We retrofit our launch and recovery system. And so it's very scalable. Here you can see how we could scale up to 6 million tons per year. That's a large amount of production. And we feel that it's significantly less expensive than the dredging approach. It also has much less environmental impact because we've minimized the noise. We are doing selective harvesting. If we see life, we avoid it. And that's a very unique technology that we have invented. So let me now come on to the final point, which is, are there any issues with LFP? And I believe there are. And these are not talked about, but one of the challenges with an LFP cell is that the voltage of the cell is pretty constant, even as the state of charge as it starts to discharge. And as a result, it becomes very difficult to estimate how much charge is left in the cells when you have a pack, and hence how much range is left. And so Tesla and others are telling people with LFP cells, please charge it to 100% every time, so that we can give you an accurate indicator of how much miles are left. If you don't do that and you just add a little bit of charge, the accuracy will be wildly inaccurate. And you may think that you have, 100 miles left, but you might only have 30 or 40 miles left. That's inherently one of the challenges of LFP chemistries, and the fact that the voltage is constant. And so we've also talked about this gravimetric energy density, the fact that these batteries are heavier. And so even at the pack level, even if you use a structural pack, you're going to get about a third less range. And that is one of the challenges, especially with North American consumers, where range anxiety is one of the reasons why people say they don't want to buy an electric vehicle. Do you really want to give up that extra range? And in cold weather, LFPs struggle even further. So you typically have to spend a lot of energy conditioning the battery pack, heating it or chilling it to make it at optimum condition. And so you could see range reduced by a further 20% or so in very cold weather. And so now you're getting significantly less range than people were expecting. Also, there are some challenges with fast charging. Now, this is a moving target. All battery technologies are improving, but historically, it's been pretty difficult to apply a large amount of current to LFP and do that without having a lot of damage and hence affecting the life, and especially when it gets cold or in hot weather. And due to the safety issues of LFP in China, they've actually banned second use. They said, we're not going to allow LFP cells to be taken out of their first use and then reused again because it's just too risky with the chance of explosions and fire. So coming towards the end of the presentation, I just want to kind of summarize. Our view is that nickel-rich chemistries that dominate today in the US market and will continue to. We don't see LFP replacing all of the market, although we do think that a mixture of chemistries are going to be used. And with the deep sea mining, with the recycle value, with IRA subsidies, we think we can actually make the nickel-rich chemistries very cost competitive, maybe even less expensive than LFP. It's very clear that because of the gravimetric energy density, you're always going to get better range, even with structural packs. The safety factors of LFP mean that you cannot ignore the chance of explosion. So you have to design a pack that mitigates against thermal runaway and the venting gas and explosion. And so at the structural pack level, I think you're still going to see about 33% more range for the nickel-rich chemistries, and also when it's cold. And then sustainability. We're not going to run out of nickel and cobalt. There's a huge amount in the ocean. We can do it without any human rights issues. We can do it with a fraction of the environmental issues, especially with our technology of using selective pickup where we preserve the habitat. So our view is we should go to an environment where we can have the least environmental impact, not the most, which is what we do today with rainforests. And with nickel rich, you don't really have any compromises. You can do fast charging. You can do it even when you don't have to charge the vehicle to 100%. And so I think my last slide coming up here. Here is some data from one of the big analysts, Roland Berger. They spend a lot of time and money analyzing these chemistries and forecasting where they are. So the first thing to say is that now in 2023 globally, about 2/3 of the market is nickel rich today. About 1/3 is iron rich, LFP. Now their forecast, which obviously doesn't factor in deep sea mining, but they're saying that even with the structure of how the market is today, nickel still remains to be about 50% of the market in 2030. We actually think that as our technology matures, as we bring on deep sea mining resources, we can lower the cost, lower the environmental impact, we can impact that. And actually, LFP may not be quite as big. But definitely all of these chemistries have a place. We're not saying one will dominate another, but the people that predict that LFP will be 80–90% of the market, we don't accept that. So thank you very much. I think I will open up to questions.
Hey, thanks, Oliver. I'm going to start with a couple of written questions that came in, and then we'll get to the hands up. Kirsten wrote, unfortunately, our oceans are not undisturbed anymore. The comparison doesn't quite work. Assumption from the graph, all seabed is equal. Kirsten, were you referring to the
pie chart?
Yeah, go ahead.
Pie chart, yeah. I think, Oliver, as much as I completely am behind your technology and think that is, the best and most sustainable technology, as far as I know, that's out on the market at the moment, I think some of what you state about the environmental impacts is a little bit naive. Your pie chart here basically assumes that our oceans are undisturbed, which they are not. And also you cannot just compare to trawling by that. I mean, trawling will happen in only a certain part of the seabed. Likewise, mining will only happen in certain parts of the seabed. So this is a little bit too simplified, I think, which has as such not much to do with your with the aim of your presentation. I totally understand, and I apologize for that. But I think you would give yourself more credit if you do these things not in such a simplifying manner.
That's fair enough, and you know, definitely the ocean is very different. You know, we see coral reefs and lots of marine life in shallow water. We see much less biomass in very deep water. But
yes,
yeah,
less biomass, but also kind of, you know, you just won't disturb, or you just will avoid the, as you said, the visible megafauna. What lives in and on those nodules, for instance, that is too small for the camera to pick up. That, you know, and the habitat will still be removed selectively and not to the same extent, but it's still, you know, there still is an impact.
Completely agree.
Not the theme of your presentation, so sorry for having.
No, I mean, you know, all mining has an impact. You know, we're not trying to claim that there's zero impact. I do believe with our selective harvesting technology that, you know, even though if we can see the megafauna, we clearly will not disturb it. But in addition, we will work with marine scientists to decide how much additional material do we just leave behind. And that, I think, is there to really help the biodiversity. You know, with the dredging, they have massive areas of no dredging, but they are thousands of kilometers away, and we know the biodiversity varies. With us, we can do it in situ. As we're mining, we can decide that we will leave quarantine areas as we go and produce. And so we're trying to do everything we can to minimize the impact, but we're never saying it's going to be zero.
Yeah. Thank you for that.
Yeah, and thank you to Kirsten as well. Kirsten participated in our scientist roundtable last week. So she's one of the scientists who are consulting with us as we're developing our equipment. So thank you, Kirsten, for coming today and for participating in that last week. Kirsten talks to us all the time. It's so great. And I learn from her every time. So now I need to learn more about this pie chart. That's what I've learned today. Okay. So I'm going to do one more question from chat that came in prior to some hands up. Kieran asked, who owns the NCM 811 chemistry using battery patent, I wonder? So I don't know a lot about battery patents, so maybe you can understand that question better than me, Oliver.
So NMC means nickel, manganese, cobalt. These are the ratios. So 811 means 8 versions of nickel to 1 of cobalt. It's not owned by any one company. All of the major battery manufacturers make these types of chemistries. The initial IP, if you like, for nickel rich was invented many, many years ago, 20, 30 years ago. And so, you know, you can go to LG, you can go to SK, you can go to CATL, you can go to Panasonic and others, and they can make you nickel rich chemistries.
Great. So we're going to move over to some hands up that came in. So Victor, would you like to go ahead and unmute yourself?
Okay, good evening. Can you hear me?
Yes.
Yes.
Yeah, my name is Victor from Nigeria. And being an Africa, I think your technology is good. It will reduce the impact we are having in DR Congo on mining, because we recently discussed in our case study in battery MBA about China resilience in battery raw material and in LFP, how China dominates the LFP market and even the equipment. Then looking at your technology, how do you think that the robot will resist harvesting seaweeds that is on the seabed? I think that will also impact on the environment as well, because some of the weeds are essential for the survival of the lives in the under the sea, under the waters. And looking at the ship, the vessel you're using, how sustainable is the vessel? What fuel is it using? Is it battery powered? And what is the amount of CO2 you're releasing by shuttling through the sea to harvest those granules, the elements you need to for this technology? Then considering the impact, the vibrations that can be impacting on the lives of animals under the water. So those are my questions.
Okay, three questions. Let me try and answer them. So seaweed, we do know at these depths there is no light that naturally reaches, and so there is no fauna. So no plants, no seaweed can grow at these depths. They could grow higher up, and that's something that all autonomous underwater vehicles have to deal with, and there are and we would do potential cleaning as part of the maintenance, but at the depths that we're going to, there is no seaweed per se down there. Question about carbon and emissions. So we are very keen to use low carbon transport. That's something that we have not yet committed on as these technologies mature. What we have committed is that we want to be net zero by 2030. So we're very keen to invest and use low carbon emission transport technologies, whether that is electric ships or whether that's hydrogen or other fuel that would be low energy. And then I forgot what the third question was. Anyone remind me?
Vibration. I was looking at vibrations.
So we are trying to minimize sound and other forms of vibration. The ships we are using will not need differential positioning. That's what generates a lot of noise, because with the dredging they have to keep the ships very, very still, and we don't need that. And so it's not really the vibration that's the issue, it's more the noise. And a lot of the noise is at the surface or at the mid-water column. And that's where the big marine life like whales and dolphins are. And so again, with our architecture, we're trying to minimize the amount of noise that is released by the vehicle, especially in the upper and mid parts of the water column. Okay,
Thank you.
Next? Thanks.
Okay, so we're gonna move back to okay, so Kieran, sorry, I'm just going to go back to this one because you already answered it. It says NMC 811, not NCM 811. Does it matter about the chemistry? No, same answer?
Yeah, I mean, different industry use NMC or NCM, they get interused.
Okay. Okay, looking at a question from George. A few questions here. Question 1, will there be any impact on carbon sink? So I'm assuming meaning at the seabed, the carbon sink within the seabed.
Yeah, we don't believe so. I mean, we're talking up to 4,000 to 5,000 meters of water. It's very, very difficult to move carbon up that distance, and there is not a significant amount of carbon stored in the nodules itself. With our technology, we're not touching the seabed directly. And even if we were, given the huge distances, it's very unlikely any of the carbon that would be in the seabed could make its way all up the water column to then enter the atmosphere.
Question 2, when impossible metals, I understand plume formation and disturbing seabed will be minimum. What about the noise and light? So noise and light from the vehicle itself.
Yeah, those are things we are trying to minimize. We talked a little bit about noise. We feel the biggest challenge with noise is actually at the surface and towards the upper parts of the water column, because that's where the big mammals live that would be impacted. Light, our vehicle does use lights, but only when actually harvesting. So when it's moving up and down the water column, which is the majority of the time, its lights are off because they're not needed. So the lights are very localized just as we pick. And we potentially could do experiments to look at what wavelengths, what colors would have the least impact to the life down there. But the vast majority of the life doesn't necessarily have good perception for light, because naturally there is no light down there.
Yeah, as Oliver said regarding the studies, there's a lot of what we're doing. If we get to the point where this is being proposed as a mining solution on a particular nodule field, there would be environmental impact assessments regarding pretty much everything to do with our vehicle and everything to do with the baseline environment, including noise and light. And those would certainly be questions that would be studied in particular. Question 3, the economics, I understand, is an approximation as actual harvesting is not attempted yet.
That's correct, but both the Metals Company and the DEME Group have put out a concept economic model, and that's what we use to put their data. We've also published our own concept economic model. There was a previous webinar given by Jason, our CTO and COO, that you can find on YouTube, that goes through the economics of our solution.
We have a raised hand from Ananta. Sorry if I'm not pronouncing your name correctly. If you'd like to turn on your mic, you can go ahead.
Thank you. It's Ananta, but I mean, you said it quite well. So hi, Oliver. I've been following you for the last couple of months on LinkedIn, and I've been very curious about what you do and how you do it. It was a really interesting video that you'd shown, and I was just curious whether you've done any pilots, or maybe a question before, what stage is your startup in? What are the current challenges that you're facing? That would be something a bit more on the the logistics operations side. But as far as the elements that you've taken to care about, not disturbing life at that level of the sea, and also you had. I was curious about the quality of the metals as well that you're mining. Compared with, I mean, from what we hear, the quality of lithium that we have now on Earth is actually quite poor. So we've actually used up most of the good, dense ore, but like we have to refine the lithium and other metals also, because they're kind of like getting even less, in density. What kind of density can we expect from the places where you mine or plan to mine?
Yeah, that's a great couple of questions. So let me talk about kind of the quality of the metal. I'm just trying to jump to this one. Yeah. So obviously these metals are elements. So nickel from one location to another, when it's in its purest form, is the same. But what varies is the grade. So when you dig out the ore, what percent of that ore contains the metal you want versus metals or waste material. And on land, it has now decreased significantly as we have done a lot of mining. And so for new mines, you're seeing ore grades at around 0.2 to 0.3%. So that means that the vast majority of all the ore that you dig out of the ground is waste, and you have to spend a lot of effort, A, digging that out of the ground, and B, processing it. One of the attractivenesses of the deep sea is that we have not done any mining, and the ore grade is incredibly high. So it's 1.3%, but if you factor in the credit for the other metals, specifically the copper, the manganese, the cobalt, it's 3.2. And that really drives the unit economics. The two biggest drivers of the economics of a mine are the ore grade and the location. Because if the mine is very, very remote, which it will almost always be for new mines on land, because we've already mined the good stuff, you've got to build all this infrastructure, and that adds a lot of cost. And the grade, it's like, how much do you have to get out and how much processing do you have to do? And so we have a very, very good story, and that's what drives our economics. Now, your previous question on where are we on our roadmap of commercialization, we've actually now built two proof of concepts, and we call them Eureka 1 and 2. That's our internal names. Eureka 1, we started to operate last year. It's a shallow water proof of concept. It can go just about 25 meters, 75 feet. It has a single arm, but it is operating fully autonomously in a lake close to our design lab. We are in the process of testing Eureka 2. This is our second generation robot. It's designed to be able to go up to 6,000 meters deep, or 4 miles. And we are now testing that in the lake, and we intend to test it in the ocean on a real nodule field off the east coast of Florida and Georgia called the Blake Plateau in the first quarter of next year. So in the next few months, we hope to have succeeded of picking up a real nodule off the ocean floor using our autonomous vehicle. Hopefully that answers your questions.
Yeah, that's very cool. I'm definitely going to continue keeping up with what you're doing.
Thank you. And the next step, maybe I can just add, is to the Eureka 2 is a great vehicle for doing marine science. It has 3 arms, but it has a relatively small payload, 100 kilograms. It's not something that you would want to put into production if you ultimately want to collect hundreds of thousands and millions of tons. And so we have spec'd Eureka 3. This is a much larger vehicle. It has 16 arms. It has 6,000 kilograms payload. And this is the version that could ultimately go into mining. And so the next step would be to build one of them, prove it works, and then to build a fleet and then start mining. Obviously, we need the permits, and our strategy is to partner with the people that already have exploration permits. They are doing environmental baselines. They've done resource estimates. And the goal would be the earliest we could be partnering would be 2026, when the technology and the permits would come together. And that's when we think we could start delivering these metals to the battery industry.
Thank you.
Yeah, and to be clear, our technology readiness for 2026 may align with permitting readiness or may not. So the 2026 timeline is very is very much about when we believe we can have it ready, and if things are ready on the permitting side, all the better. And if not, then that comes as it may. Ray in the chat said, there are environmental costs with everything humans do. From a public messaging perspective, simple is better because most people don't spend much time researching such things. How should impossible metals methods of mining be compared with existing land-based mining on numerical scale? If land-based mining is 10 out of 10 for environmental damage, what can your seabed mining method be described as numerically? Oliver, I would be happy to take this question if you'd like, since it's from sort of a sustainability perspective, but if you'd like to take it, of course.
Yeah, maybe I'll just give a very brief preamble, and that is, you got to be specific, right? You know, you could have a mine in Canada that's doing everything to be as sustainable as possible, getting commitments and doing a really good job. You could have another mine that's in Africa that's owned by Chinese that is not doing a great job and is using child labor. So I think you have to be very specific when you answer this question. But Becky, over to you.
Yeah, certainly that's one thing that would bring into it, sort of like what mine, right? There's a lot of mines that are in compliance with IRMA, which is the its responsible mining standards, which are quite stringent. Additionally, I think this is difficult to say because deep sea mining isn't happening right now. So there's always things that you don't know, and that's why there's something called adaptive management. So say a deep sea mine is permitted, they have management and mitigation measures in place to prevent significant impacts. At that point, that monitoring and those management programs, they adjust over time as more learning is done. So while on land, we have a long history of mining, and so the environmental risks are fairly well known. In the deep, that's one of the key concerns that's typically brought up. So the point being, we do everything we possibly can to prevent impacts, and then there's adaptive mitigation as it continues, and that learning is continued. So to provide a number at this point is probably not possible, but the purpose is to be responsible in what we're doing and to continue learning and continue decreasing impacts over time. But a number would be, even working in this, and I worked in land-based mining previously, I would not be able to provide you a number. But I know that from what I've seen, our team is doing everything possible to have as low impact as possible. Oliver, does that sound reasonable to you?
Yep, that's great. So I think we're kind of out of time. I want to thank everybody for joining. We are planning a January webinar, which will be on kind of subsea technology. So look for that. And thank you, everybody, for joining us. Really appreciate your time. Thanks, guys.